This is Lecture 1 in Module 11 from the book Problem-Solving Guide for Mechanics and Thermodynamics. The subject is thermal expansion and thermal conductivity. Here's a disclaimer. You're welcome to pause the video and read it. Here are some problems that you should know how to do before you take the exam on thermal expansion and thermal conductivity. A 12-foot long section of steel railroad track goes from a temperature of 5 degrees at night to 25 degrees Celsius at noon. What is its change in length as a result of this temperature change? A 30 centimeter by 40 centimeter rectangular piece of aluminum foil is taken from room temperature, about 20 degrees Celsius, to 200 degrees Celsius. What is the change in area of the aluminum foil? A 2-foot by 3-foot glass window has a thickness of 1/4 inch. It is 10 degrees outside, 20 degrees inside. What is the rate of thermal energy transfer through the glass? That, of course, is thermal conductivity. The first two examples are thermal expansion. Here's another problem, a bit more challenging. An aluminum rod of length L and diameter D is placed end to end with a copper rod of length L and diameter D. There it is. The left end of the aluminum rod is kept at 0 degrees Celsius. The right end is kept at 100, and there's insulation around the rod, so no thermal energy leaks out the curved sides. What is the temperature at the interface between the two metals? What is the temperature right here? Okay, here's the lecture. This module contains two straightforward concepts, the concept of thermal expansion and the concept of thermal conductivity. Let's start with thermal expansion. When objects are heated, the atoms in the object get a little further apart. The size expands. So let's think about what the equation would look like for the change in length of a rod. Delta L. What's delta L for a rod when you heat it? What does it depend on? It has to be proportional to the change in temperature. The bigger the change in temperature, the bigger the change in length. So there should be a delta T in there somewhere. It's also proportional to the original length of the object. If you have a long object, it's going to change more in length than a very short object for the same temperature change. Finally, it's got to be dependent on the material from which there's some kind of material property that tells you how it expands with temperature. It's called the thermal expansion coefficient, the coefficient of thermal expansion. The symbol for this is lowercase alpha. The full equation is the change in length is a function of the thermal expansion coefficient of the material, the original length, and the change in temperature. That should make sense. You shouldn't have to remember that equation. The units of thermal expansion coefficient are fractional change, delta L over L, per degree. If you want, you can put the L in the bottom. And then you have delta L over L as alpha delta T. So the fractional change has no units, they're both lengths. The units of alpha are usually written as 1 over C, degrees Celsius, or degrees Celsius to the -1 power, something like that. Here are some sample thermal expansion coefficients, and the thing to notice here is that they're small, and you know they're small. Right? If you heat up something, it's not going to grow substantially. 10 to the -6th, 10 to the -5th order of magnitude, brick, glass, iron, aluminum, zinc. So let's do a problem with the concept of thermal expansion. An aluminum pizza pan, circular, has a diameter of 14 inches. What's the change in its area when it's taken from room temperature at 20 degrees Celsius to 200 degrees Celsius? So this is a change in area. We want to know the change in area. Our equation gives us change in length. We can use any length we want. We can use the radius, we can use the diameter, we can use the circumference. That's what the equation is good for, a change in a linear dimension. So let's use the radius. Let's calculate the change in radius when you heat up that pizza pan. The original radius is 7 inches, the diameter is 14 inches. The change in radius is given by that equation, We know what aluminum is, 23 times 10 to the minus 6th. The original length that we're dealing with is 7 inches. The change in temperature is 180. It goes from 20 to 200. We can calculate that to L, 0.029 inches. Pretty small. So now the radius is 7.029 inches because the original radius was 7 inches and we calculated the change in radius. Now we can calculate both areas. The original area of the pan, it's pi r squared. It's a circle, 153.94 square inches. The expanded area of the pan, it's got a radius of 7.029 inches, pi r squared, 155.22. And to get the difference, the change in area, we just subtract these. So the answer is 1.3 square inches. That's the change in area. Thermal expansion is an important consideration for engineers. Catastrophic failure can occur if thermal expansion is not considered and accounted for. Temperature in Cleveland can vary by more than 50 degrees. Very cold in the winter, hot in the summer. So metal bridges have expansion joints to account for the increase in the length of the bridge on a hot day. They look something like this. On a hot day, those teeth will come in. On a cold day, they will retract, and cars will still be able to drive on that road. Railroad tracks have gaps in the rails to account for an increase in length on a hot day. So there's a gap right here. When it's really hot, these things are going to be close. When it's cold, they're going to be separated more. Pipelines have these U-shaped compensators. So here's a U-shaped compensator. And the pipe actually is not attached. It can slide back and forth here. Otherwise, it would fail. So this, in the summer, when it's really hot, these two ends get closer together. And when it's cold, they get farther apart. And this prevents any catastrophic stress. Big slabs of concrete in a driveway or, for example, an airport runway have expansion joints to account for the increase in the size of the concrete on a hot day. If you don't leave sufficient gaps in the railroad tracks, they can buckle. Here's an example. A hot day in New Jersey. This buckling caused a derailment. When iron wants to expand, there's not much you can do to stop it. It will actually bend. A tremendous force caused this track to bend. There are a couple of neat applications involving the difference in the thermal conductivity of two metals. In some thermostats, there's a very thin bimetallic strip. Sometimes it's a coil. Here's a bimetallic strip, copper on the bottom, steel on the top. Copper has a significantly higher coefficient of thermal expansion than steel, so copper responds more to changes in temperature than steel does. If it's cold, copper shrinks more. If it's hot, copper expands more. There are electrical contacts above and below the strip. Which of the two contacts should turn on the furnace? The top one or the bottom one? Well, if it's cold, the copper is going to shrink, and steel is going to shrink, but the copper is going to shrink more than the steel. So when the copper shrinks, it's going to pull this thin strip downward. So the bottom one should turn on the furnace. If it's hot, the copper will expand more and curl the strip up, and that might turn on the central air conditioning. The bimetallic coil was invented by master clockmaker John Harrison to compensate for the fact that changes in temperature change the stiffness of the clock spring. So he made a spring that was impervious to changes in temperature by using a bimetallic coil. Before electronic clocks, the best timekeeper was a pendulum clock. The pendulum would swing back and forth, but the period of a pendulum depends on its length. And if you have a metal rod as a pendulum with a weight at the end, the length is a function of temperature. It will expand if it's hot. It'll shrink if it's cold. And of course, when John Harrison was around, there was no central air conditioning. If the house was cold, the pendulum would be shorter and the clock would be fast. If the house was hot, the pendulum would be longer, the clock would be slow. The effect for each swing is small, but after a day, the clock would be significantly off. So to do this, to figure this out, he invented the gridiron pendulum, and this was really clever. Here's the gridiron pendulum. The blue represents the iron, and the yellow represents the zinc. If it's hot, both the zinc and the iron expanded. Now what the zinc did is the zinc lifted up. It pushed up the pendulum bob when it was hot. Zinc has a thermal expansion about 2.5 times bigger than iron. So the yellow expanded 2.5 times more about than the steel. So he adjusted the length of the rods, so the whole length of the pendulum did not change. He would stand in the doorway between two rooms in the middle of winter. One was freezing cold, the other room had a roaring fire. So the temperature difference between the two rooms was tremendous, and he would stand between the rooms and listen to the clocks tick to make sure that they were in phase. And he adjusted those lengths to get that. With today's indoor heating and cooling, the bimetallic gridiron is no longer necessary, but grandfather clocks still have a non-functional gridiron to honor the brilliance of master clockmaker John Harrison. So there's the gridiron right there. It's non-functional, of course. It's just a bunch of rods for decoration, but that gridiron honors John Harrison. Okay, now thermal conductivity. We're going to switch gears. That was thermal expansion. In Module 10, we determined the equilibrium temperature of two objects when you put them together. You drop a hot piece of metal in water. What's the equilibrium temperature? We did nothing to figure out how long it would take to get to equilibrium. So here we investigate the rate of thermal energy transfer when the temperature difference between two objects is constant. So if we have an aluminum bar and we place one end in an ice bath, kept at 0 degrees Celsius, and the other end in a pot of boiling water, kept at 100 degrees Celsius, how much thermal energy is flowing through the bar per second? What's the rate of thermal energy transfer from the boiling water, hot water, to the cold water? So here's what it might look like. An aluminum bar connecting these two. Thermal energy is going to flow this way by the atoms. This aluminum is hot, this aluminum is cold, and thermal energy will be transferred to the cold side. The units of thermal energy transfer, joules per second. And a joule per second is a watt, power, the rate of energy transfer. So let's think about what the rate of thermal energy transfer should be. What parameters determine the rate at which thermal energy is transferred from the hot side to the cold side? What is Q over T? What should it be proportional to? Well, it's got to be a function of the material in which the rod is made. If it's aluminum, it's going to be pretty good. If it's wood, it's going to be pretty bad. This material property is called the thermal conductivity. The symbol is lowercase k. So far we have a k there. And so there's going to be some other things. What are they? If the rod is fatter, if the pipe is bigger, it should transfer thermal energy at a faster rate. So if it's just a wire, very thin diameter, it's not going to transfer a lot of thermal energy. So it's the cross-sectional area of that pipe. So it's an area, A. The bigger the area, the bigger Q over T. It's inversely proportional to the length. If the rod is long, the temperature gradient is not big, and that's what drives the thermal energy transfer. If the rod is short, you're going to get a lot of heat flow. So that L goes in the bottom. It's inversely proportional to the distance between the two temperatures. Finally, obviously, it's the temperature difference. The bigger the temperature difference, the bigger the heat flow. If the temperature is very close, you're not going to get a lot of heat flow. So delta T belongs in there. And there it is. That's what the thermal energy transfer is equal to. The property of the material through which the thermal energy is being transferred, the size of the pipe, the temperature difference, which is driving the thermal energy transfer, and the distance it has to go. That's it. Should make sense. Here are some typical thermal conductivities. There's a huge range here. Silver's good, copper's good, aluminum's pretty good, cast iron's not so good. So cast iron, if you put a cast iron pot on a stove, it takes longer to heat up than copper. Stainless steel, not good at all. If there's really hot gravy on Thanksgiving, you should be able to tell whether the spoon that's in the gravy is silver or stainless steel. If it's silver, you better be careful. You might burn your fingers. If it's stainless steel, the spoon's not going to be that hot because the thermal conductivity is low. Brick, oak, air, not good at all. Argon, if you have glass doors to go out to your patio, it's very likely that there's a layer of argon in between the two glass panes because that prevents thermal energy transfer through the window. So let's do a problem. Here we have some boiling water at 100 degrees Celsius. The Bunsen burner will keep it at 100 degrees Celsius. Here's some ice cubes in water. They're thermally connected with a rod, a metal rod, diameter 2 centimeters, length 5 centimeters. The rate at which ice is melted by the thermal energy coming from the boiling water through the metal pipe is 45 grams per minute. 45 grams of ice is melted per minute. What is the thermal conductivity of the material from which the rod is made? What's the K for this rod? So to start, we need the amount of thermal energy needed to change 1 gram of ice at 0 to 1 gram of water at 0. That was module 10. It's the latent heat of fusion of water, 334 joules per gram, 334,000 joules per kilogram. Same thing. We're melting 45 grams every minute. The thermal energy transfer through the rod must be 45 times the amount for 1 gram every minute. So there's the flow rate, 45 times 334 joules per minute, and we convert that to watts, 251 joules every second. So now we have Q over T in the units that we need, and that's equal to K A delta T over L. And I think we have everything, or we can get it. We have to calculate A. The diameter is 2 centimeters, the radius is 1 centimeter, the area is pi r squared, the cross-sectional area, and we plug in and we get 3.14 times 10 to the minus 4th square meters, and now we're ready to go. We have to calculate K. We have one equation, one unknown. There's the area. The temperature difference between the ends of the rod is 100 degrees Celsius. That's what's driving the thermal energy. And there's the length in units of meters, 5 centimeters, 0.05 meters. And we can calculate K. 400 watts per meter per degree Celsius. So looks like copper. Copper is 400. Let's make it copper. Okay, there we go. Copper rod. So that's it for the concepts of thermal expansion and thermal conductivity. The equations involved should make sense to you. The change in length is alpha, thermal expansion coefficient, times the original length, times the change in temperature. Of course it is. The flow rate is the thermal conductivity, times the cross-sectional area through which the thermal energy is flowing, times the temperature difference, which drives it, divided by the length. Now you have to practice by solving problems to develop your skill in solving problems involving thermal conductivity and thermal expansion.